So virtual network technologies are overlaid onto the existing operational network infrastructure. Therefore, the network continues to function as it did before the virtualization, but now has virtual networks overlaid on top of it. The endpoints using the network could belong to the original network or to a virtual network. This provides a clear path to a phased migration and support for groups that do not require a dedicated virtual network. Virtualization technologies primer theory. This is the last point of the virtual network. Network device virtualization, data path virtualization. One of the characteristics of a network device virtualization is that it provides what are essentially private communication paths between members of a group over a shared infrastructure. This creates two requirements for the network infrastructure. Traffic from one group is never mixed with another. For sending and receiving traffic over shared links, tunnels can guarantee data separation. Network devices need to enforce group separations in their internal memory, routing table lookups, access list processing, or net flow statistics gathering. Each virtual network has a separate address space. This requirement is derived from the fact that virtual networks offer the same characteristics as a physical network. Address space and forwarding within it are the two of the most basic aspects of any network. Network device virtualization, the first problem to solve is how to virtualize a forwarding plane in a way that meets the requirement for address and traffic flow separation. Depending on the type of device, the virtual separation can go by the following names: virtual LAN, virtual routing and forwarding, and virtual forwarding instance, VFI, and virtual firewall context. Layer 2 virtual LANs. Virtual LANs are a good example of a piece of virtualization puzzle that has been around for quite some time. A virtual LAN is a logical grouping of ports on a switch that form a single broadcast domain. Ports in a VLAN can communicate only with other ports in the same virtual LAN. How a given switch does, this is implementation dependent. But a common solution is for the switch to tag each frame with a virtual LAN number as it arrives on port. When a frame is sent to other ports, the output hardware copies the packet only if it is configured with the virtual LAN number carried in the frame. On an Ethernet switch, there is typically a single MAC table which maps ports to MAC addresses. To support virtual LAN, the MAC table has a field for the virtual LAN number on which the station was discovered, as demonstrated in example. This is how the table address table is stored for the virtual LAN. You have the destination address, address type, virtual LAN numbers, and destination port number, which port you are connecting to. The layer 3 VRF instances. VRF, a VPN routing and forwarding instance. A VRF consists of an IP routing table, a derived forwarding table, a set of interfaces that use the forwarding table, and a set of rules and routing protocols that determine what goes into the forwarding table. Unlike the virtual LAN scenario where an extra column in the MAC table is adequate, a VRF partitions a router by creating multiple routing tables and multiple forwarding instances. Dedicated interfaces are bound to each VRF. A simple logical representations of a router with two VRFs, red and green. The red table can forward packets between interfaces E1 by 0, E 1 by 2 and S 2 by 0. This is where the red table forwards packets and the green tables forwards between interfaces, Ethernet 4 by 2, S 2 by 2 and S 2 by 1. An interface cannot be in multiple phase VRFs at the same time. This is how the VRF instances are stored. Red indicates default routing address, interfaces, which interface is used, Ethernet ports, these are the Ethernet ports and the serial port. Green indicates that this is the default RD and the interfaces that it connects to is the serial ports and the Ethernet port. So the mapping is shown here, interface, IP address, VRF and protocol. Forwarding information base and routing information base. I hope everything is very clear. Right? It sounds so clean and very simple. We all are masters in networking, aren't we? So I think instead of me carrying out, I can ask any one of you to come and explain out here. You all must have done it in your BSc or whichever backgrounds you all are coming from, might be networking. So it would be very much appreciated if you all can come and share your knowledge also. Anyone? Anyone from here wants to come and share? If you have covered in your BSc or wherever, I mean masters or anything, anywhere there where you have covered up the networking, it would be very much appreciated, because even I am not getting the book related to the network virtualization. If you all have the book, or you all have read through it or had gone through the classes, you can come and share it. It will be very much appreciated, because it's a knowledge sharing. Basically, the more you share, the more you gain. That is what we keep teaching our kids. The more you share, the more you gain. So if you can come and share, it will be very, highly appreciated. Does anyone wants to volunteer on this? Anyone, I'm happy. I would be very happy if somebody can come and volunteers it, because I really don't have this book. Anyone having a PDF of this? है किसी के पास PDF book? You have virtual network? You have it or you don't have it? I know networking is not our cup of tea, may not be, but you never know. Tomorrow one of you may want to take up this networking as It is interesting. We only see from the, 1,000 feet above the sea that we are getting an access, and sometimes what we say, we keep cribbing. Why aren't we getting a proper access of the network? Do we see the other side of it, how this complete network architecture has been implemented for us, how the service providers are working? We are a step ahead. We are a master's students. Tomorrow we will be a PhD holder. So we have to always think us 2 steps ahead. So always think what is going on behind your scene. Be it algorithm, be it statistics, everywhere, even this networking. If you have seen it, ad hoc network and sensor network, that is completely based on your whatever the algorithms that you have been studying right now. Dejecta's algorithm, all the algorithms, the same algorithms has been implemented. The software in itself does not work. The network software also is based on the algorithms that you all are studying. Without that algorithm, even you cannot do anything with it. What you will do? What you are going to write? All these forwarding tables, logical tables, wherever your information's IP addresses, when this request has to be forwarded, to whom it has to be forwarded, how are we going to group it, what is the cost effectiveness of the network. So everything is, each of the thing is based on the algorithms that we are studying it. Nothing is independent of each other. All are linked with it. So if you have studied those algorithms, it will be very easier for you to implement it in the networking algorithms also. So let me continue with it. So we have 2 routing tables for the network virtualizations. Forwarding information base and routing information base. Forwarding information base is a database of information used to forward packets. When a packet is received on a routed interface, the router looks up the destination address in the FIB to find the next hop for the packet. The FIB structure is particularly efficient for resolving longest prefix matches, and Cisco IOS resolves all route redirections so that a single lookup can yield the entry for the next hop of a packet. Because it contains both layer 2 and layer 3 information, the FIB can be updated by several sources such as routing protocol, address resolution protocol updates. And the RIB is a memory structure that contains classic routing data. The RIB can contain recursive routes. If a packet destination is not in the FIB, the router punts a packet to a slow processing path and resolves the destination's next hop using the RIB. This is how the routing table is there for whenever we will have the network. Keep this in red, which is written. This is a syntax for accessing, checking whether the tables of the FIB and the RIB. So some of the commands to view the FIB is this: show IPCEF, IPCEF, VRF, red. So during our practical session, we can check with these 2 commands. Traffic processing happens according to the same rules as on a device with no VRFs. Traffic enters the router, the ingress policy is applied, routing and forwarding lookup occurs, the egress policy is applied, traffic is forwarded. Virtual and logical router. A logical router uses hardware partitioning to create multiple routing entities on a single device. A logical router can run across different processors on different cards of a router. All the underlying hardware and software resources are dedicated to a logical router. This includes network processor, interfaces, and routing and forwarding tables. Logical routers provide excellent fault isolation but do require abundant hardware to implement. And a virtual router in other case, one is a logical router and one is a virtual router. Uses software emulations to create multiple routing entities. The underlying hardware is shared between different router processes. In a well-implemented virtual router, users can see and change only the configuration statistics for their router. This is a virtual net router and this is a logical router. VRF awareness. A VRF aware feature can be configured to refer to routing and forwarding information from a specific VRF and understand that only certain sub-interfaces can be used with certain VRFs. Without this information, the feature uses the global table. For example, to assign an interface to a VRF, the basic interface IP address command was modified to take a VRF name parameter and become IP address VRF name forwarding. If all features required for a particular applications are VRF aware, you can use VRFs to emulate a VR and hence provide virtualized device functionality. A VIF is a service-specific partitions on a switch that associates attachment circuits in the form of VLAN with virtualized switch interfaces. VPLS is a layer 2 LAN service offered by service providers to connect Ethernet devices over a WAN. The customer devices, call them customer edges, are all Ethernet switches. However, the service provider uses a layer 3 network running multi-protocol label switching to provide this service. The device on the edge of the service provider network is called a provider edge. Its role is to map Ethernet traffic from the customer LAN to multi-protocol label switching tunnels that connect to all other provider edge that are part of the same service instances. The provider edges are connected with a full mesh of tunnels and behave as a logical switch called a VSI. The virtual provider LAN service as a collection of Ethernet ports connected across a WAN. The VSI is a set of ports that form a single broadcast domain. In many ways, a VSI behaves just as you would expect a regular switch. When a PE receives an Ethernet frame from a customer device, it first learns the source address as would any switch before looking at the destination MAC address and forwarding the frame. If the port mapping for the destination MAC address is unknown or it's a broadcast, the frame is sent to all Ps that are part of the VSI. The Ps use split horizon to avoid creating loops, which in turn means that no spanning tree is needed across the service provider network. Once again, there is a need to define and manage groups of isolated ports and tunnels on a switch. The VLAN construct is too limited and a VRF is strictly a layer 3 affair. So, it is necessary to come up with a new virtual device structure for VPLS called a VFI. This is a VPLS technology. A pseudo wire is a tunnel, and this broad, the thick line represents a VLAN that runs across the multi-protocol LAN services backbone and connect the VSI on the PE devices. The C switches think they are connected to the trunk on VLAN 100. The thin lines between PE and the other actual pseudo wires define the I2 VFI statement. This is the configurations of the VFI. Virtual firewall context. Device virtualization is not limited to switches and routers. It is also considered as a firewall device. For essentially economic reasons, you might want to share a single firewall between multiple different customers or network segments. Each logical firewall needs to have a complete set of policies, dedicated interfaces for incoming and outgoing traffic, and users authorized to manage the firewall. Many vendors provide this capability today and undoubtedly have their own well-chosen name for it, but on Cisco firewalls, the term context is used to refer to a virtual firewall. Unlike VRF, VFIs and or VLANs, a context is an emulation of a device. Firewall contexts are a little unusual in the way they assign a packet to a context. All the partitions we have seen up to now have static assignment of interfaces. A firewall module looks at an incoming packet's destination IP address or Ethernet VLAN tag to decide which context a packet belongs to. All the firewall needs is for one of the two fields to be unique. So either each context has a unique IP address space on its interface or the address space is shared, but each context is in a different VLAN. The switch binds the VLANs to VRF blue at the top and VRF red. The firewall has two different contexts. The blue one receives all frames on VLAN 101 and the red one gets VLAN 102. In this way, packets from the outside that belong to VLAN 101 go through a different set of firewall rules than those belong to VLAN 102. So, network device virtualization summary. True device virtualization allows resources to be allocated to tasks or applications. We looked at 4 different primitives that virtualize the forwarding paths on switches: VLAN and VFI for layer 2, VRF for layer 3, and context for firewalls. Each of these functions slightly different. VRFs have the most extensive tie-ins with other features. This is the last virtualization path, data path. It has got layer 2 802.1q trunking. Inserts a VLAN tag on Ethernet links, has a vital attribute of guaranteeing address space separations on network interfaces. Obviously, this is a layer 2 solution and each hop must be configured separately to allow 802.1q connectivity across a network. Because a VLAN is synonymous with a broadcast domain, end-to-end VLANs are generally avoided. Generic routing encapsulations. GRE provides a method of encapsulation, arbitrary packets of one protocol type in packets of another type. The data from the top layer is referred to as the payload. The bottom layer is called the delivery protocol. The GRE allows private network data to be transported across shared possible public infrastructure, usually using point-to-point tunnels. Although GRE is a generic X over Y solution, it is mostly used to transport IP over IP. GRE is also used to transport legacy protocols such as Internet Work Packet Exchange and Apple Talk over an IP network and layer 2 frames. This is a header of the GRE. The second 2 octets of the header contains a payload protocol type encoded using the Internet assigned numbers authority, Ethernet numbers. IP is encoded as 0x800. The simplest possible expression of a GRE header is a protocol type field. All the preceding fields are typically 0 and the subsequent ones can be omitted. GRE routing encapsulation is an encapsulation mechanism. There is no control protocol, no session state to maintain, no accounting records and so forth. And this conciseness and simplicity allows GRE to be easily implemented in hardware on high-end systems. The time-honored mechanism for detecting tunnel reachability problems is to run a dynamic routing protocol across the tunnel. Routing protocol keep alives are dropped if the tunnel is down, and the routing protocol itself will declare the neighbor as unreachable and attempt to route around it. You can lose a lot of data waiting for an RP to detect a problem in this way and reconverge. Cisco added a keep alive option to its GRE implementation. GRE's lack of control protocol also means that there is essentially no cost to maintain a quiescent tunnel active. The peers exchange no state information and must simply encapsulate packets as they arrive. Furthermore, like all the data path virtualization mechanism, the core network is oblivious of the number of tunnels traversing it. All the work is done on the edge. IPsec provides a comprehensive suite of security services for IP networks. IP security was originally conceived to provide secure transport over IP networks. The security services include strong authentication, encryptions, and key exchange mechanisms. They use a security algorithms. IP security peers maintains a database of security associations. A security associations is a contract between peers which defines the following: the specific encryptions and authentication algorithms used, such as triple DES data encryption standard. The IP security protocol services encapsulating security payload, key material needed to communicate with the peer. The security association is negotiated with an Internet protocol security session is initiated. Peers maintain a list of essays for inbound and outbound processing. The value of the SPI is shared between peers. It is one of the things exchanged during IPsec session negotiations. At the protocol level, there are two IPsec headers, AH and ESP. There are two ways to encapsulate Internet protocol security packets. One is through tunnel mode and other is through, this is the tunnel mode, new IP header, IP security header and IP header data. So this is the encrypted form area, and we have the transport mode. In the transport mode, IP header is above. There is no new IP header. Internet protocol security requires a lot of negotiations to bring up a session, so much so that there is a separate control channel protocol called Internet Key Exchange, used to negotiate this essay between peers and exchange keys material, IKE, which is the Internet Key Exchange. During confidential data exchange, a session key is used to protect unidirectional traffic may need to be changed regularly, and IKE is used to negotiate new keys. IKE traffic itself is encrypted, and in fact it has its own essay. Most of the parameters are fixed. 56-bit DES for encryption, message digest 5 MD5 algorithm or secure hash algorithm hashing. And the last one is that LT2 TPP version 3. This is another protocol, consists of a components to bring up, maintain and tear down sessions and the capability to multiplex different layer 2 streams into a channel. You have two types, which is the session ID and the cookies, and most of you are aware of this session ID, how the session ID is stored and the cookies are stored. The difference between